On April 13th, 2029, an asteroid named Apophis will pass closer to Earth than our own geostationary weather satellites. NASA and global space agencies have verified its trajectory and issued a firm guarantee. Apophis will safely miss our planet by roughly 32,000 kilometers. Looking at this scale comparison, Apophis measures roughly 375 meters across, dwarfing structures like the Eiffel Tower and holding far more mass than a typical football stadium. We are completely safe from this specific rock, but observing an object this massive at such close range forces us to evaluate the margins of our safety. What if the initial calculations had been wrong? In space, asteroids constantly absorb solar heat. As they rotate, they radiate it back, creating a microscopic continuous thrust known as the Yarkovsky effect. As this trajectory line shows, if that thermal thrust, or a minor collision with stray space debris, were to shift the asteroid's path by just a fraction of a degree, that 32,000-kilometer safety net would vanish. To understand the physical consequences of that vanishing gap, we will initiate a strict chronological simulation of a direct impact, beginning exactly 6 months before 0 hour. Mapping this disastrous timeline reveals where our current planetary defense systems work and where they fail. T-6 months. Observatories sound the initial alarm. Mission control centers run the new data, confirming the deviation has locked Apophis onto a collision course. Verification requires immediate international consensus. Planetary defense teams in Europe and around the globe synchronize their tracking networks to cross-check the math. This size comparison highlights the primary problem at T-3 months. Humanity has deflected an asteroid before. NASA's DART mission nudged the 160-meter Dimorphos, but Apophis carries far more mass, requiring a magnitude of kinetic force that a standard probe simply cannot generate. T-1 month. With deflection options failing to secure a safe orbit, governments are forced to outline evacuation zones. Global supply chains break down, and financial markets freeze as institutions realize the impact radius is no longer theoretical. The announcement of impact zones would trigger a total economic seizure. As insurance companies go insolvent, real estate values hit zero, and resource hoarding paralyzes supply chains. The systems that keep modern life running would break down months before the actual physical strike. The countdown hits zero. Apophis breaches the atmosphere, traveling between 12 and 20 kilometers per second. This chart calculates kinetic release. The Hiroshima detonation produced roughly 15 kilotons. Apophis generates up to 1,500 megatons. Even the 1908 Tunguska event, which flattened 2,000 square kilometers of forest, produced only 15 megatons. It barely registers against the Apophis strike. A direct strike on land excavates a crater 5 to 7 kilometers wide. The resulting shock wave ripples outward, flattening structural foundations across a 100-kilometer radius. Statistically, an ocean impact is far more likely. The kinetic energy transfers directly into the water column, displacing millions of tons of ocean and driving massive tsunamis toward coastlines. In both scenarios, millions of tons of pulverized rock and vaporized water are ejected into the upper atmosphere. This debris layer blocks solar radiation, collapsing global temperatures and halting agricultural production. The resulting years of darkness and freezing temperatures would end large-scale agriculture and global power grids. The world that eventually emerges from the dust would be unrecognizable. Fortunately, the simulation ends there. Our current observations confirm that Apophis will safely pass Earth in 2029 without striking the surface. Humanity has actively engineered a planetary defense network, specifically to ensure these calculations remain accurate and that we have tools ready if they ever change. The primary countermeasure is the kinetic impactor. By calculating an asteroid's precise orbit, engineers launch a high-mass spacecraft to physically ram the object, transferring momentum to nudge it off course. For targets identified earlier, there is the gravity tractor. As visualized here, a heavy spacecraft hovers parallel to the asteroid. Over several years, the microgravity between the two masses gently pulls the rock into a safe trajectory. If time is critically short, engineers can deploy a nuclear device. The goal isn't to shatter the rock, but to detonate nearby, using the intense radiation blast to vaporize one side of the surface and push the asteroid away. Whether we use kinetic force, gravity, or nuclear radiation, the physics demand one resource. Success requires years of advance notice. That lead time is generated by tracking stations around the world, scanning deep space to keep millions of near-Earth objects cataloged and monitored. Because they tracked Apophis so accurately, its 2029 arrival provides a massive opportunity for research. Spacecraft like NASA's OSIRIS-APEX are already en route to intercept the asteroid, allowing us to study its composition up close. On April 13th, 2029, anyone with a clear sky will be able to look up and watch a 375-meter rock glide safely past our planet with the naked eye. We know exactly where this rock will be because we mapped its path. Humanity is actively tracking the hazards of the solar system, ensuring we survive them.